Welcome to lecture number 6 for ECE 341, Random Processes. In this lecture, we look at combinatorics applied to a dice game, Farkle. Now, Farkle is kind of a fun game, play with your friends, neighbors, kind of a beer and pretzel game. It's a dice game where you roll dice and you try to score points. Now, the ways you score points is each 5 that you roll is 50 points. Each 1 is 100. 3 of a kind is 100 points times the value, except for 3 ones, that's 300. If you roll 4 of a kind, that's 1,000 points. 5 of a kind, 3,000. 6 of a kind, 3,000. 1 to 6 straight, 1,500. 3 pair, 1,500, and so on. So the way the game is played is you roll the dice, and the rule is that every time you roll, you have to score points. If you roll and don't score any points, you say Farkle, your turn is over, and you lose all your points. So as you're rolling, you can decide, do I roll again or stop? If you stop, you get to keep your points. If you roll again, you have a chance of making more points, but you have the chance of getting 0 points. So let's kind of show you how Farkle's played. So in Farkle, you start with 6 dice, like so. When it's your turn, you roll the dice. And I have to score points. So the previous slide, we talked about how to score points. A 1 is 100 points, a 5 is 50 points, 3 of a kind is points, and here I've only got 1 die that scores. So if I keep the 1, I scored 100 points. All the dice that didn't score, I can roll again. So here I have only 1 die scored 50 points. At this point I can decide, do I stop with 150 points and take the 150 points, or roll again? Now suppose I roll again. I take all the dice that didn't score, roll them, and I've got 1 die that scored. That's 50 points. Again, I can decide, I can stop with 200 points, or roll again. And, okay, I've got 2 5s. I could keep 1 5 and roll 2 dice, or keep 2 5s and roll 1 die. If I roll again, I didn't score any points. So at that point, I lose all my points. I get 0 points, next player's turn. In addition, if this last die did score a point, if all 6 dice score, I get to start over, keep all my points, and roll 6 dice again. So the strategy in Farkle is to figure out, when do you stop rolling and keep my points? When do I keep rolling? For example, here I've got 400 points for 50. What I would do is I would take the 400 points and roll 3 dice. There's 550. I would stop at 550. So can we calculate what you should do in Farkle? So that's what we'll be doing in this lecture, using combinatorics to determine when you should stop, when you should keep playing, as well as combinatorics to figure out the odds of different types of hands. For example, what are the odds of rolling 4 of a kind, 5 of a kind, 6 of a kind, straights, and so on. So that's what we'll be doing in this lecture. Now, as I mentioned before, the strategy in Farkle is to know when to stop, when to keep rolling. If you stop, you get to keep your points, but you lose the opportunity to get more points. If you keep rolling, you might get more points, but you might lose everything. So, in order to determine whether you should keep rolling or not, you need to calculate odds. So let's take the case where I have 5 dice that scored. I'm going to roll 1 more die. If I roll 1 die, there are 2 ways to get 6 points. Here we're just using numeration. The ones that score would be a 1 and a 5. So 2 in 6 chance of scoring a point, 4 in 6 chance of getting Farkle, losing all my points. Now if I score a point, and I'm rolling 1 die, all 6 dice have scored, and I can start over again with 6 dice. And that's worth points. Kind of my experience, that's worth about 300 points if you get to roll all 6 dice again. Not exactly sure that's right, but ballpark. Let's just say 300 or 600. What I'm going to do is calculate the expected return. If I roll 1 die, how many points do I expect to gain? times the probability of success, minus how many points I expect to lose if I'm not successful, times the probability of failure. Now, if the expected return is positive, I should keep rolling. If it's negative, I should stop. That's one way to calculate whether I should keep going or not. So the expected return is how many points I'm going to get if I roll one die. If I roll one die, I could score a 1. That's 100 points. Plus all the dice are scored, and ballpark, that's about 300 points when I roll all 6 dice. So I'm going to gain about 400 points 1/6 of the time. I could roll a 5. If I roll a 5, that's 50 points, plus all the dice scored. That happens 1/6 of the time, and 4/6 of the time I lose everything. So let's just say I had X points, that's how much I'm risking. The expected return then is 125 minus 4/6x. Set that equal to 0, that's the break-even point. So that says that if I have 187 points or less, keep rolling. I don't have anything to lose. If I had more than that, I should stop. So that's when rolling one die. How about if I'm rolling 2 dice? Again, 4 dice have scored. I've got 2 dice left. Do I roll those 2 dice or do I stop? Well, doing the same procedure, let's calculate the odds of scoring points. Here again, I can use enumeration. There are 36 ways to roll 2 dice. 4 and 6 of them score on both dice. 16 and 36 score on 1 die. And 16 and 36, nothing scored. That's a Farkle. I lose my turn. So let's calculate the expected return. If I roll 2 1s, that's 200 points, plus all the dice scored, 300 points. That happens 1 in 36 times. If I roll a 1 and a 5, there are 2 ways to do that out of 36 rolls. That's worth 150 points, 100 for the 1s, 50 for the 5, and all dice scored. If I roll 2 5s, that happens 1 in 36 times. That's worth 100 points, 2 5s are 50 points each, plus 300 points for all the dice scoring. A single 1 could roll. I could score a single 1. So look at all the cases where there's a 1. There are 8 instances of that. A 1 is worth 100 points. 8 instances where I rolled a 5. That's 50 points. And 16 instances where I scored nothing. I lose all my points. So adding all that up, the expected return is 83.33 minus 16 over 36 times x. If I set that equal to 0, find the break-even point, I get 187. So again, the magic number is 187. If I have 4 dice that scored, and I've scored less than 187 points, keep rolling. Otherwise, stop. How about 3 dice? If I'm rolling 3 dice, the probability of no dice scoring is the numbers that don't score are 2, 3, 4, and 6. So there's 4 numbers that don't score out of 6, 4, 6. All dice have to be one of those numbers, so 29% chance of rolling all 2, 3, 4s, and 6s. Now there are 216 different ways of rolling dice, so that means there's 64 ways to roll numbers that don't score. And there's actually 4 of those that do score. If I roll 3 4s, 3 6s, 3 3s, 3 2s, that's 3 of a kind, that scores. So really there's only 60 ways of rolling 3 dice and not scoring. So the probability of no scoring is 60 and 216. Probability of scoring is 156 and 216. Now the number of points I get would be, if I score, if I get 3 of a kind, that's worth 300 points plus all the dice scored. That happens 1 in 216 times, 6 cubed. If I have 3 2s, that's 200 points plus all the dice scored. 3s, 4s, 5s, and 6s. So that's the expected return for rolling 3 of a kind, plus there's other ways to score points. I could roll a 1 1 5. There's 3 permutations for that. Basically, the 5 can go in any one of these 3 spots. So it's 3 and 216, and that's worth 250 points. 100 for the 1s, 50 for the 5s, and all the dice scored. 155, there's 3 permutations that have that. Scores 200 points plus all the dice scored. 11X, there are 12 combinations. So basically there are 4 numbers I can choose for X. That goes in 1 of 3 spots, so 4 times 3 is 12. That's where the 12 comes from. And 2 ones is 200 points. 15X, there's 12 combinations that do that, 150 points. 55X, 12 combinations that do that, 100 points. 1XX, again, the number of ways that can happen is there are 4 numbers for X, 4 numbers for the second X, and the 1 can go in any 3 spots. So 4 times 4 times 3 is 48. 48 points of getting a single 1 and 2 garbage numbers, 100 points. 48 ways to get a 5, that's 50 points. And 60 ways to get a Farkle, I lose all my points. Okay, so adding all that up, that's 91 points minus 60 over 216 times X. Set that equal to 0, and I get X equals 330. Meaning if I have less than 330 points, keep rolling. So based upon that analysis, here's how the game of Farkle would go. I roll the dice and see what's scored. Okay, so I've got 300 points, and I could take 350 and stop. That's more than 187. I should stop at that point. Or I could just score the 300 and reroll 3 dice. I would do that. So I'll have 300. 300 is less than 387, so I should roll 3 dice. Rolling 3 dice, I got unlucky. That's a Farkle. Turns over. Next player. I'm going to roll all 6 dice, start their turn. Okay, here's a 1. 1 scored. Let's roll 5 dice. Roll 5 dice. And there's 150. I'll roll 4 dice now. There's 250. I could say 350 and stop, or 250 and roll 3 dice. I do 250 and roll 3 dice. Woohoo! All right, 600. So now I have 850 points. All the dice have scored, so I get to start over. I have 850 points. And 3 5s is 500. That's 1350. Roll 3 dice. 1350 is more than 380. I should stop at this point. That's basically how the game of Farkle plays. Once you get to 10,000 points, everybody's got 1 more roll, and the game's over. So using combinatorics, I can figure out when I should keep rolling and when I should stop. Next, let's look at what are the probabilities of getting different types of die rolls. If I roll 6 dice, I can score a couple different ways. I get 6 of a kind, 5 of a kind, 4 of a kind, and 2 of a kind, 4 of a kind, and so on. What's the probability of rolling each of those combinations? Well, one approach is enumeration. I'm going to go through every combination of die rolls. So this is nested for loops. The first die can be the numbers 1 through 6, second die, third, 4, 5, 6. Here are all the different types of die rolls. I will then count. What's the frequency of 1s, 2s, 3s, 4s, 5s, and 6s? If I have the highest number is 6 of a kind, that's 6 of a kind. If it's a 5, 5 of a kind. Highest is 4, next highest is 2, 4 and a 2. 4 less than 2, 4 of a kind. 3, 3, 2 triples. 3 less than 3, 3 of a kind. 2, 2, 2. 3 pair, and so on. So in MATLAB, I can run through every permutation. And the nice thing about MATLAB is it's actually pretty fast. Here I'm going to go through, again, every permutation of dice, and then check what kind of they are. You can also check for a straight. If there are no pairs, that's a straight. I've got the numbers 1 through 6. And then display when you're done. So grinding through every permutation, that took 0.979 seconds. Again, enumeration isn't all that bad. It is no finesse, just brute force. And with MATLAB, sometimes brute force works really, really well. So here is the correct answer. Here's how many ways I can roll 6 of a kind, 5 of a kind, 2 triples, and so on. Let's see if I can calculate those numbers using combinatorics. So starting out with 6 of a kind. 6 of a kind, I have 6 dice all the same. Using combinatorics, I would say there are 6 numbers for x, choose 1. There are 6 spots to place the x's, choose 6. So the answer is 6. There are 6 ways to get 6 of a kind. That matches up with MATLAB. 5 of a kind. From enumeration, there are 5 ways of doing that. Think about how I would calculate 5 of a kind using combinatorics. Okay, to do that, what I would say, there are 6 different die numbers for x, choose 1. There are 6 places to place the x, choose 5. So that places the 5 x's. Now there are 5 remaining values to choose for y, choose 1. There is 1 spot for y, choose 1. Multiply all that out, I get 180. So that's how you calculate the probability of getting 5 of a kind. Let's try 4 of a kind. So 4 of a kind would be 4 x's, y and z. Y and z have to be different. If they're the same, that's a different combination. That's 4 and 2. Pause the video and see if you can calculate the probability of getting 4 of a kind using combinatorics. And the answer you should get is 1800. We got that using enumeration. Okay, so let's try that. Here is actually an incorrect way of doing it. For the x's, I have 6 numbers to choose for x, choose 1. There are 6 places to place the x's, choose 4. Now for the y's, I'm going to say there are 5 numbers to choose for y, choose 1. There are 4 numbers to choose for z, choose 1. So if I check that, 6 choose 1 is 6. Times 6 choose 4, 5 choose 1 is 5, 4 choose 1 is 4. That's actually correct. So that's one way to do it. Another way to do it, what I would actually do, since y and z have the same frequency, I would say there are 5 numbers to choose for y and z, choose 2. For the y's, there are 2 locations, choose 1 for y. There's 1 remaining spot, choose 1 for z. That also works out to 1800. So actually either way works. If I do it the second way, times, and choose m, 5 choose 2, times 2 times 1, also 1800. Either way works. I would do the second way. Kind of use the pattern we had back in poker. Whenever numbers have the same frequency, I handle them together. So that's probability of getting 4 of a kind. Let's try 3 of a kind. Now for 3 of a kind, there's actually 2 different ways of doing it. I could have 3 of a kind, a pair, and a single, or 3 of a kind and 3 singles. Either way, the total has to add up to 14,400. That's what we got with the numeration. How do we get there? Well, let's start with the 3 of a kind, a pair, and a single. So for the x's, there are 6 numbers, choose 1 for x. There are 6 locations to place the x, choose 3. That placed the 3 x's. Now, there are 5 remaining numbers, choose 1 for a. There are 3 locations to place the a's, choose 2. And then the b's. There are 4 remaining numbers, choose 1 for b. 1 choose 1. So if I do that in MATLAB, that'd be 6 times 6 times and choose m of 6 choose 3 times 5 times 3 choose 2 is 3. 3 times 4 times 1. 7,200. That's half the answer. The other half of the answer would be 3 x's, a, b, and c. So to do that, I would say there's 6 numbers for x, choose 1. There are 6 locations for x, choose 3. Since a, b, and c have the same frequency, I would say there are 5 remaining numbers, choose 3. That picks out the a, b, c. There are 3 locations to place a, choose 1. 2 locations to place b, choose 1. And 1 location to choose c, choose 1. So that all added up is m2. m2 is 6 times and choose m of 6 choose 3 times and choose m 5 choose 3 times 3 times 2 times 1. Also 7,200. Add them all together, I get 14,400. So that's how I calculate the probability of 3 of a kind, which is 3 singles and 2 and 1. How about 2 triples? That'd be like 3 4s and 3 2s. I should get the answer 300, so let's try to do that with combinatorics. Okay, what I would do here, x and y has the same frequency, so there's 6 numbers, choose 2. That pulls out the x and y. For the x's, there are 6 locations to place the x, choose 3 of them for the x's. Now there are 3 remaining locations, choose 3 for y. So what that works out to is m is, and choose m of 6 choose 2 times and choose m of 6 choose 3, and 3 choose 3 is 1. 300. Next, let's look at 3 pairs. If I have 2 x's, 2 y's, 2 z's, like 2 4s, 2 1s, 2 2s, there should be 1,800 ways of getting that. Can I calculate that using combinatorics? So again, pause the video, see if you can calculate that. Okay, picking up then. X and Y and Z have the same frequency, so I do those together. There are 6 numbers, choose 3 for X, Y, and Z. There are 6 locations for X, choose 2. There are 4 remaining locations for Y, choose 2. There are 2 remaining locations for Z, choose 2. So let's see if we get the right answer. So M would be, and choose M, 6 choose 3, that pulls out the X, Y, Z, times, and choose M of 6 choose 2 for the X's, times, and choose M, 4 choose 2 for the Y's, and 2 choose 2 is 1. 1,800. So with combinatorics, you can use combinatorics not just for card games, but for dice games. With dice, it's a little bit different. What you do is, of the 6 values, when they're at the same frequency, I do n choose m. For example, with the 3 of a kind, there are 6 numbers, choose 3 for the x, y, z. Then use the spots. How many different locations are there? How many of them do you fill with that value? It's a little bit tricky using combinatorics, but the results should be identical to enumeration, and it takes a lot less time. When you have a lot of die rolls, you might want to use combinatorics. So that is lecture number 6 for ECE 341, Combinatorics applied to dice games like Farkle.